some more information about the triangles and when you're given the tan of the angle, what to do. So if we look at the triangle here, the angle A, it'll work out as 45, but it has an opposite of 1, an adjacent next to the angle of 1, and a hypotenuse of 1.414. Now, if I was to get the shadow of that, so shine a light, get the shadow of it, and if that shadow is a magnification of it, then you'd have an identical triangle in terms of the angles. You'd still have the angle A there, you'd have a right angle in the bottom left-hand corner, and you'd have a third angle unlabeled up at the top, which is identical in both triangles. But the sides would be different. Now, these are similar triangles, and if you look, the opposite is 4 and the adjacent is 4, and actually they're the same value. So on the right-hand triangle you've got 4 and 4, on the left-hand triangle you've got 1 and 1. So they're the same angles. And then if you look at the hypotenuse on the right-hand triangle, it's 5.656. If you divide that by 4, you get 1.414. So the two triangles are in ratio. These are called similar triangles, and the sides of one triangle are in the same ratio as the sides of the other triangle. So one of them is a magnification, but the angles are the same. And this is important to understand for what we're doing in applied maths at the moment with regard to the angle stuff. Notice that tan A is the same for both triangles as well. The one on the left is 1 over 1, the one on the right is 4 over 4. Both give you an angle of 45 because tan of 45 equals 1. Okay, so let's have a look at this. If you were told tan of an angle is 5/12, that isn't telling you that the length of the opposite is 5 and the length of the adjacent is 12. It's telling you that the ratio of the lengths is 5:12. So opposite over adjacent there for tan. So like if we had a triangle like that, you can see that the opposite isn't 5 at all, the opposite is 10. However, if you compare that to the tan A is 5/12 above, the opposite actually in the triangle that's drawn is twice the value that's given in tan A. So that means the adjacent will be twice that. The adjacent will be 24 in that case. But still, if you got tan of A, you'd get 10/24, which if you cut it down to an equivalent fraction is 5/12. Let me give you another two examples. So in this case, the tan of the angle is 5/12, and then if we look at the triangle on the right, tan of A is equal to 20 over the adjacent. 20 over the adjacent should be equal to 5/12, so the ratio should be maintained. The 20 is 4 times the 5, so that means the adjacent is 48. And 20 over 48, when you cut it down, is indeed 5/12. Now, of course, there's always a special case where the opposite is the same as the value given tan of the angle, and in that case, then the adjacent will be 12. But remember that just because you're given tan of the angle in fraction form doesn't mean that the numerator or the denominator are equal to any lengths. It just means the ratio of the two lengths given, in this case opposite and adjacent for tan, are in the ratio of whatever is given in the question, 5/12 in this case. Okay, so have a look at that. So the values in the fraction aren't lengths or aren't forces. What they are, they're the ratio of a pair of lengths or the ratio of a pair of forces. So let's have a look at this one. Now, if I give you tan A there, you can say tan A equals that length over that length. And that is true because the ratio will be the same. So that length over that length will equal tan of the angle. Now, I've got the components of the weight there. If I move one of them to that position, tan of A is equal to that force, that force length or that magnitude of that vector or that size of that vector over that size of the vector as well. But you can see that that triangle here is not the same as that triangle. The only thing they have in common is that they're similar triangles. They're triangles that are in the same ratio as one another. So the three angles inside the plane triangle, the pink triangle even, and the vector triangle are identical. Now I am rambling a little bit, but this isn't planned. I'm just going to keep going with the rest of it. So what to do with the tan A thingy? So if tan A is equal to a fraction or a decimal, the first thing you need to do is get the inverse tan of the fraction or the decimal. then I'd ask you to get the sine and the cos of that angle. So the goal there, if you're given tan A is equal to something, get the angle and then get the other two trigonometric formula for sine and cos. Once that's done, I'd be suggesting to put into that formula, and remember the opposite and the adjacent in the vector triangle will be the values of the components. And look, I'll just draw your attention to the opposite and the adjacent. What they actually are is the length of the hypotenuse multiplied by another ratio. So you can even see there the opposite in the adjacent. The opposite is not equal to the opposite in the tan fraction. The adjacent isn't equal to the adjacent in the tan fraction. They're equal to things that are a little bit more complicated. Now, let me give you one example. So I've got my opposite and adjacent identified in my vector diagram. Tan A is 5 over 12. That means that I need to get the inverse tan of 5/12. So A equals the inverse tan of 5/12. That gives me 22.6 degrees. My next step is to get the sine of 22.6 degrees. I've written that in fraction form, you'll get it in decimals, and get the cos of 22.6 degrees. There's a misprint there. That'll give you a fraction of 12 over 13. Okay, so we've got the inverse tan, we've got sine and cos. Now it's time to get the opposite and the adjacent. For the opposite, we fill in the value for the hypotenuse, which is W, and we fill in sine of the angle. Sine of the angle is 5/13, multiplied by W gives me the opposite of 5W over 13. Repeat that for the adjacent, and you're done.